Hi, everybody, and welcome back to Chee-Tash. My name is Chris, and today we're going to be talking about the book Clean Code, Chapter 13, all about concurrency. If you guys remember last time, we talked about Chapter 12, which was about emergence. And in that chapter, we kind of went through some simple design rules that were, according to this author, Kent Beck, and his 4 rules for simple design. And we talked about how code should run all tests, it should contain no duplication, it should express the intent of the programmer, and it should minimize the number of classes and methods. And today we're going to talk about concurrency. And what is concurrency? Well, simply put, concurrency is threading. If you guys have worked in Java, I don't know if it's like they're not like completely synonymous. Maybe like threading is a way to do concurrency, but I think there's other ways to do concurrency. But basically doing something and then having it return at a later time, or doing multiple things and having them return at a later time. And the first slide is going to have a pretty good definition of what I'm saying here. It's a decoupling strategy. So what concurrency is, this is the best way to put it, is that it's a decoupling strategy where you separate what gets done from when it gets done. So you can have multiple different processes running at the same time and then have them finish or get the results of the thing that they are processing at different times. So there's single-threaded and there's multi-threaded. Java allows for multi-threading. JavaScript, through async awaits or promise chains, can allow for concurrency as well, or you separating what gets done from when it gets done. So single-threaded code, as you can imagine, is just way easier to do than multi-threaded code, because with multi-threaded code, as we're going to see, it opens up Pandora's box for potential bugs, potential issues with your code if you're not synchronizing it. So if multiple threads can depend on each other, and that could possibly corrupt the data when they both depend on a shared object. But we'll get to that in a couple slides. Concurrency can be very useful. It can make your code look like a bunch of mini computers talking to each other, as the author states in this chapter. And one example of concurrency is when using servlets. So Java servlets are a way to make HTTP requests. So there are ways to make basically an API. So you have endpoints that you can execute HTTP requests to. So your gets, your posts, your puts, your deletes, etc. And these servlets can be executed asynchronously, because if you think about it, if you do have a web server, you're going to have customers, clients, what have you, multiple customers and clients hitting your web server, sometimes at the same time. So they have to be able to execute irregardless of all the other customers who are pinging your web server. So each servlet is decoupled from the rest of them. And these servlets can help to make and handle all these HTTP requests. So again, like I said, it allows for multiple clients to ping your server. And the servlets that you have created that are being used in your web server are managed by the servlet container, something like Tomcat. And you might see this when you run a Java program and it says, Tomcat server started at port 8080. I think that's like a common thing that's mentioned when you run a Java program. And that container is managing the servlets, the collection of servlets, and it's managing which servlet should execute which request. And it's kind of all managed within this self-containing, no pun intended, container. And that container is essentially doing concurrency. It's managing which servlet gets the request, and it's separating threads that might get started sooner rather than some that might get started later. And here on the right, we have an example of this where, just a simple example, we have this Echo servlet. It's got a method that I'm sure it inherits from HTTP servlet class. It's probably something that is required that it implements here. So you have a do get, and then when you initiate this do get, you echo back the client's request. So this is one of the parameters here in this method, request.get parameter message, response.get writer, and then you can print out, oh, you said this, etc., etc. So just a simple example of a servlet. And you can imagine that you'd have do get, you'd have a do post, you'd have a do put potentially. And this is essentially the makings of a web server and creating endpoints and ultimately creating an API. So those are servlets. Single-threaded. Yes, single-threaded, what we were speaking about in the very first slide, and comparing it to multi-threaded, and how single-threaded is just way more simpler of a concept. Just one thing has to finish before the other thing starts. And this is like most of what I write in, for my current role at my company is, and we do have some concurrency with using futures and using asynchronous programs or asynchronous code to call and run queries that are going to finish at different times, but at the end be joined into one object. But single thread is just way simpler. Just think about it like this. One thing has to finish before the other. And in multi-threaded, you have multiple things that can start and finish at different times. Is concurrency better? Is multi-threading better over single-threaded? It depends. It's not really always the case like that. And that's, I think, one of the myths and misconceptions that Robert C. Martin talks about, and he has a whole section about this. So one of the myths and misconceptions, we'll just go down the list here. Concurrency always improves performance, and sometimes it does. If you write it cleanly, I think it can, but still sometimes, because if you don't write clean code and if you don't have clean concurrency, then you could end up having deadlocks. You could end up having corrupted data because data's not getting updated, especially if you share an object between the multiple threads that are being run in your program. You could have times where that object is not being updated properly and the count gets messed up. We're going to see that in like a simple counter example, I think, on one of the upcoming slides here. So concurrency always improves performance, sometimes only when there is a lot of wait time to be shared amongst the threads. Another myth or misconception, design of concurrency does not change when writing concurrent programs. Your design has to change. And we're going to talk about we're going to mention later how your non-threaded code should be separated out from your threaded code. And it's kind of hearkening back to the single responsibility principle, where your threaded, multi-threaded code, your concurrent code, should be single responsibility. You should really only do one thing, and then keep your non-threaded code separate so as to adhere to the single responsibility principle, so your classes only really do one thing. If you're going to write concurrency, have one class that does the concurrency. Don't have it spread out randomly throughout your entire project. Next, understanding concurrency issues is not important when working with a container such as web or EJB container. Think of a web or EJB container. This is essentially like the servlet example that I gave in prior slides ago. You still have to understand concurrency, even when, like I said, those servlet containers manage it for you, because you can still run into issues. You can still run into deadlock. Even though these containers are managing all these requests pinging your web server for you. Next, concurrency incurs some overhead both in performance as well as writing additional code. That is true. That is very true. You're going to have some extra overhead, and you're going to have to, how should I say, you're going to have to make up for the fact. Not make up for the fact, but you're going to have to take into account concurrency and the performance of concurrency when you're writing your code. Next, correct concurrency is complex. Again, 100% very true. Concurrency bugs aren't usually repeatable. That is a myth. That's not a myth. This does happen sometimes, and they're called one-off bugs. We're going to talk about this a little bit later, too, in the chapter. They mention about one-off bugs, which make it hard to test concurrency because of the fact that multiple things are happening at the same time, where when you do get a bug, it's hard to imagine it being a bug because it just happens once. And then when you try to run your program again, the bug might not happen again, just because of the behavior of concurrent code. But they're saying that these are actually bugs. They're not just one-off, like fluke errors. There's something to be studied and looked at if you come across them. And then lastly, concurrency often requires a fundamental change in design strategy. 100%. I just mentioned that a little bit ago. But there are ways to still write clean code even though you are using concurrency, mainly with just using the simple principles that we were talking about for a lot of this book, namely single responsibility. Classes should really only do one thing. If you have methods, your method should really only do one thing. And limiting the size and the scope of your concurrent code and not have it totally intertwined and hard-coded within the rest of your code. It's better to have it separated out into its own classes, its own files. Make it a little more readable that way. Make your code a little more organized, etc. So this was an example of some of the issues with writing concurrent code. And I mentioned this counter example earlier. So you have this counter class where you're going to be able to increment the count. So how do you do that? So you read the current value of the count that is being set here in this class. You're going to increment it, and then you're going to write it back to the count variable. And then down here, you can go and get the counts. You have a getter. Well, if I start two threads here, right, they're going to go until they hit 1,000. So because you see these for loops here, starts at 0. We're going to go until it's 999, right? So 1,000 here, 1,000 here. And it's going to increment every time, right? So you're going to do counter.increment. So you're going to increase it by 1. But notice that these two threads are acting on the same counter object that we created up here. So when you start each thread and then when you join is essentially saying that, okay, we're going to conglomerate or we're going to aggregate the results of T1 thread and T2 thread. And they're acting on the same counter. So when I print the count down here, one might expect that the counter might be 2,000, which would make sense. You're looping, and for each iteration of the loop, you're incrementing, right? But odds are there's a chance that the count ends up being less than 2,000 because of the fact that these two threads are operating on the same counter. And if I had to pick like a main point of this chapter, if you guys can take away one thing from this chapter, one thing from this video, it's that there's potential for data corruption when you have threads operating on the same object, in this case, counter. So what do I mean by that? So you could have an instance where this is getting incremented at the same time that either this is getting incremented or this is reading the count. So they could potentially not be in lockstep. One thread could be slightly later than the other. So you could have this one incremented. This one might be on maybe increment where the count equals, let's say, 3. This one could still be stuck at 1. So when it reads it, it's saying 1. This one's on 3, right? This one goes to then increment, and it's going to get the count, which maybe 3 was the previous iteration, but maybe now it's getting the count and it's 1 because this one just updated it to 1, maybe because it's a little bit behind, right? So this goes from 3 to now 1, and then it increments it, so now it's 2. And you can, I don't know if I'm 100% explaining, or I'm explaining this the best way I can, but hopefully you guys can kind of get the picture in your head. Basically, the fact that one thread might be behind the other, and one thread might update the count to a number that the other thread has already eclipsed. So essentially, it kind of goes backwards. Because this one's behind, this one's going to read the number according to the thread that is behind. And all of a sudden, you would think that this would be 2000, but it might end up being like 1990 something because it got behind and it got updated to an incorrect value. Or not necessarily an incorrect value, but a value that is not coinciding with what what you think the value should be. Because I think the threads are doing their job, but they're just slightly not in lockstep with each other. They're slightly one's behind over the other. And it's like I say here. So perfect summary of this. It's possible that both threads read the count variable at the same time, as I was saying in the previous slide. So after getting modified, some updates might get lost, so you could have a result that's less than 2000. Essentially, those threads are not atomic, and atomic is another key vocab word of this chapter that is mentioned. I had to look this up because I've heard of atomic, because there's a atomic class, I believe, in Java. It's like atomic long, and I always wondered what that meant. So atomic means that it's either fully completed or not started at all. It's instantaneously working from the perspective of the other threads, and it's preventing syncing and race condition issues. So essentially, atomic means that either something's fully completed or not started at all. So those threads are not atomic in that one is not waiting for the other one to finish necessarily. But how do you do that? You can use synchronization. So you can label your methods with the synchronization keyword so that when you have multiple threads acting on it, one thread is going to need to start and finish before the other thread starts. And that's how you prevent those syncing issues on the same object. But an even better way to do it is don't have multiple threads acting on the same object. We're going to talk about copies a little bit later in the presentation. So how do you defend against stuff like this? Well, like I said, single responsibility principle. And if you guys remember, we've mentioned it multiple times within this book. And the single responsibility principle means that a method, a class, or a component should only have one reason to change. So it should really only have one job. And this is no different when you're writing concurrent code. So concurrent related code has its own life cycle. It should really only do one thing. Concurrent code is challenging on its own. Don't make it more difficult by not writing it as cleanly as you can. Keep concurrency stuff, concurrency related stuff separated from your other code, and it's going to do wonders, and it's going to go a long way in making your code more organized and understanding what's going on in your code when you do potentially end up having issues with your threading, multi-threading, and concurrency. Next, another defense principle is that you can limit the scope of data by, like I said, using the synchronize keyword when working on the same object. So if you share data amongst many different threads, the more likely it is you'll forget to protect one or more of those places. There will be duplication. It will be difficult to determine source of failures. All that is true, but if you share data when using threads, make sure to utilize this synchronize keyword, which essentially is going to tell your code, hey, this thread that is running this method needs to complete, start, and finish before another thread runs this method. And this is as simple as just this, public synchronized increment. So if you use this in my previous example a couple slides ago, I think that this would help to solve the issues of updating the count. And chances are you probably will get the count of 2,000 that you're looking for, with each thread running the loop 1,000 times and then incrementing the count +1 each time. But again, another principle is that instead of using a synchronized keyword, which has its issues on its own, it's not a general, fix all. It's not going to solve all your problems to use the synchronized keyword. It's probably sometimes better to use copies of data. So if you are going to share data amongst threads, it's better to use copies of objects instead of the actual object. So in the example that we used earlier, we were multiple threads were updating the single counter object. But it'd be better to use copies of that object when you're sharing the data amongst all those different threads. So you use the copy, you collect the results from the multiple threads, then you merge the results in a single thread. And like I said, this might be a better option because of the potential gridlock caused by the synchronized keyword. Because again, it sounds good to use synchronized and say, okay, this thread's not going to start until this thread finishes with the process. But think about if you have a very intensive operation and all of a sudden you're waiting on one thread to finish, it could potentially cause your program to run for a very, very, very long time. And then lastly, threads should be as independent as possible, kind of, again, going along with some of the other points we were saying just moments ago. Each thread should exist in its own world. You should attempt to divide data into subsets that can be operated on by independent threads. So don't rely on a single object in your threads. Each thread should exist in its own world. And next slide here, I have an example of using defensive copies. So instead of sharing the reference of an object amongst the threads, share a copy of it. And this can be seen in this example where we have this shopping cart where you're going to be able to add items to your shopping cart. So the shopping cart contains a instance variable of a list of strings of items. When you call add item, it's going to be able to add it. But look at here. Look at the difference between shopping cart and the counter class that we had earlier. Counter class had a getter where it could go and return the count of your class. Excuse me. Shopping cart has another getter, same getter, where it's going to return the items list, but it's returning a copy of it. So it's creating a new array list every time. So in your main method here, down at the bottom, you're adding items to the shopping cart. And then in another thread, you're going to get the items from the shopping cart. And look at the difference here. When you're going to get the items from the shopping cart, you're getting the copy of the list. You're not getting the list itself. And this turns out to be a little bit better, a little bit cleaner, because you're going to get a copy of the list, which is not going to be updated, or is not going to be updating in real time. If we didn't do this copy of the list and we just returned items, then again, we could have the issues that we were experiencing with Counter, where the items list might not be completely up to date. But when we create the copy of it, then any sort of item that's going to be added to it, it's acting on the actual items list, not on the copy. So if one thread gets behind, right, if adding items to the list as what is happening in thread 1 down here, if that all of a sudden gets behind, and then you show the items list, it's not going to be the most up-to-date list. But if you show them the copy of it, that's going to be the most up-to-date version on the list of the list of items, and you're not going to experience any sort of modification to this while the first thread might still be running. I don't know if I'm quite explaining that. Hopefully you guys get what I'm saying there, and how much I want to say, yeah, how much better, how much cleaner it is to use the copy. Essentially, so you don't get a situation where items is being updated or is behind in this whole thing. Is behind thread 1. Like if thread 1 is not exactly up to date in adding items. Let's continue to the next slide. Know your library. So this was just a quick section where there's multiple different libraries that you can use with concurrency. I think the main one is java.util.concurrency, concurrent, something like that. So just some things to consider that Robert talks about is use thread safe collections. These are like your concurrent hash map is a thread safe collection. Then there's like a couple other ones too. Use an executor framework for executing unrelated tasks. Use non-blocking solutions when possible. And just be careful because several library classes are not thread safe. Like if you use just a regular hash map, not thread safe. That's why there's advocate for concurrent hash map. And actually, yeah, I have that example down there. java.util.concurrent package. Okay, so I was right on that one. So you can use these as thread safe collections when you're operating on data. You can use a concurrent hash map, a semaphore, or a countdown latch. It's just some examples there. So here's an example of a concurrent hash map. The issues that, again, we were talking about in the last shopping cart example, or that we were talking about in the counter example earlier on in the slides, concurrent hash map is going to be much, much better in that regard. It's going to be able to keep track of the threads and allow for the data to be the most up to date, whereas a regular hash map is not going to be able to. So in this example, you've got one thread running for 1,000 iterations. You've got another thread running for 2,000 iterations, and you're putting items into these hash maps, and then you have a hash map size, right? Well, the regular hash map, again, might run into the same updating issues, whereas the concurrent hash map is going to be able to run lockstep between these two threads and not run into the same sort of updating issues, because it's going to be able to organize between these two threads running. Whereas if the hash map, you're going to run into the issue like we did with the counter, where hey, one counter might update while the other counter is still behind in incrementing. So the update might get updated to a number, like instead of 5, it might update back to 4, as an example. And that could potentially, similar thing could potentially happen with the regular hash map. But if you use the concurrent hash map, it's going to be able to organize in that regard. You should see concurrent hash map size here. You should see that be 3,000. You should. And then the regular hash map, I mean, again, it should be 3,000. It would make sense because you're putting a key plus I and then the actual number I. Or excuse me, this would be for 2,000. I'm sorry, 2,000, because this is starting at 1,000. So you should see both sizes be 2,000, but I don't know if this hash map, the regular hash map, will be 2,000. And who knows what the value is going to be at key 100. This is where potentially things could get messed up, and it might be less than 100. Key 100 might be 98 or something like that. So just as an example. And then knowing your execution models. Guys, I'm actually, because we're at 30 minutes, I wanted to keep this one short, and then we're still only about halfway through the slides. So I'm going to keep this video short. We're going to make this a 2-part chapter on concurrency. And I know concurrency can get kind of confusing, but maybe this will be good to split this up into 2 videos. If you guys have any questions, definitely let me know. We'll discuss it in part 2. But in part 2, we're going to talk about some of the different ways to do concurrency. So there's, and we talked about creating multiple threads, yes, but you can specifically, there's models of, there's a producer-consumer model. There's a reader-writer model. We're going to talk about that in part 2. We're going to talk about testing concurrent code and using thread.sleeps, thread.priority, etc., using those static thread methods to specifically tell your code to wait or to run one thread over the other, etc. And we'll talk about these some more key vocab words here. But thank you guys so much. I want to thank the guy who commented and had some constructive criticism, and I really, really appreciate him doing that. One of the constructive criticisms was the video, the small video of me recording myself in the corner, and how it was blocking the slides. So in this video, I didn't put that because I realized, oh yeah, that actually does cut out some of the slides, and it makes it hard to see some of the stuff, especially when I'm writing like a lot and there's a lot of stuff, especially towards the bottom. Sometimes the little video in the bottom right corner cuts things out. So that was one of them. And then the other thing was just me being a little more better organized, not having as many spelling mistakes in the slides, and actually knowing the material. So I appreciate him saying those things. Other than that, guys, thank you so much for listening. We'll be back next time, part 2 of chapter 13 on concurrency. And we got a new interview coming out tomorrow, on Monday. So thank you guys so much for listening. My name is Chris. This has been Chee-Tash. Take care, everybody.